We will now continue our discussion of the spherically distributed charge. Remember that we have a volume charge density that depends on our location in space. For r less than capital R over 2, it is linearly increasing with r, and for r between capital R over 2 and capital R, it is alpha times 1 minus r over capital R parentheses squared. Otherwise, it is 0. So in part A, we have determined alpha in terms of Q and R. Now in part B, using Gauss's law, derive an expression for the magnitude of the electric field as a function of R. Do this separately for all three regions and express your answer in terms of Q. So we're going to start with R less than or equal to capital R over 2. So in part B, the first region of interest is R less or equal to capital R over 2. All right. Our charge density, volume charge density in this region is given as 3 alpha R divided by 2 capital R. So let's check. It was 3 alpha R divided by 2 capital R. So that's the charge density we will use. Now we know what alpha is in terms of Q. So we will substitute that for alpha. So we have 3R divided by 2 capital R, 2 capital R, multiplied with alpha, which is from part A, 480 capital Q divided by 233 pi capital R cube. So that's what we have found in part A. Now this 2 will make this 480 240, and 240 multiplied by 3 is 720. So we will have for the charge density 720 capital Q times R divided by 233 pi capital R to the fourth power, because we have R cube and R here. Now we know the charge density in terms of capital Q and capital R. Now we can use Gauss' law, the closed surface integral E dot dA, the total electric flux through this spherical distribution of charge is E times 4 pi r square. That's the surface area of the sphere with radius r, where r is less than capital R over 2. And according to Gauss's law, this is the charge enclosed, Q in, divided by permittivity of free space, epsilon 0. All right. So this is 1 over epsilon 0, 1 over epsilon 0, integral from 0 to r. So we're inside the Gaussian surface. The charge density rho r prime multiplied by dV. So we're integrating all of the charge distribution inside this spherical Gaussian surface to calculate the total charge inside the Q enclosed by this Gaussian surface. So this is equal to 1 over epsilon 0, 1 over epsilon 0. And for the charge distribution, we have 720 Q, 720 capital Q divided by 233 pi capital R to the fourth power. And for dV, we have 4 pi r prime square dr prime. So this is 4 pi. Now we have to integrate from 0 to r. The charge density is 720 q r prime divided by 233 pi r to the fourth power. So we have 1 r prime here. And from 4 pi r prime square, we have an r prime square dr prime. So once again, for dv, we are substituting, or dv prime, let's say, to be more specific, 4 pi r prime squared dr prime. We're using this r prime dummy variable because we already have r in the limits of the integration. Okay, so this is going to give us 720q, capital Q, divided by epsilon 0, 233 pi. Pi is already cancelled here. So this pi gets rid of this pi. So we no longer have a pi at the bottom. Capital R to the fourth power. And from the integration, result of the integration, we have 4 r prime to the fourth power over 4. But this is going to be evaluated at r. So we will have r to the fourth power. So this is going to be the charge enclosed divided by epsilon 0. On the other side of the equation, we have electric field times 4 pi r square. So let's substitute that here. We have E times 4 pi r square. That is equal to 720q divided by 233 epsilon 0 capital R to the fourth power and R to the fourth power. Remember that we had R to the fourth power divided by 4 that got rid of this 4 here. Now we have R square on the left hand side and r to the fourth power on the right hand side. So this is going to become r square, and that will give us our final answer for the electric field. Electric field in the region, the radial distance r from the center is less or equal to capital R over 2. We have 720 divided by 233. Now you can see that we have 4 pi on the left side. So 1 over 4 pi epsilon 0 is k. So I'm going to substitute that for Coulomb's constant. So we have k capital Q divided by capital R to the fourth power, and we have R square in R hat direction. So it's going to be radially outward. This is the electric field in the region R less or equal to capital R over 2. So here we have utilized Gauss law, and we have obtained, by substituting for 1 over 4 pi epsilon 0 Coulomb's constant, we have obtained this result. Now, we will move on to the next region for capital R over 2 less or equal to R less or equal to capital R. We have the charge density rho of R equals alpha times 1 minus R divided by capital R parentheses squared, where for alpha we will substitute the answer we have found in part A of the problem. So for alpha, I will substitute 480 capital Q divided by 233 pi capital R cube. And then I have 1 minus R divided by capital R parentheses squared. So let's double check. This was the alpha value we found in part A. Okay, now we are ready to write Gauss law. The closed surface integral E dot dA for r greater than or equal to capital R over 2 is once again E times 4 pi r square. Why? Because the electric field is in r hat direction. It's only a function of r and it's going to be parallel to the area vector, which has magnitude 4 pi r square. And this is equal to the charge enclosed Q in divided by epsilon 0. And that's going to be equal to the total charge in the region r less or equal to capital R over 2 divided by epsilon 0 plus the charge that is in the region between capital R over 2 and R. So we will have alpha divided by epsilon 0, the integral from capital R over 2 to R, 1 minus R prime, 1 minus R prime divided by capital R parentheses squared, 4 pi R prime squared dr prime. So that's our dV value here. So we're writing rho dV. Since rho changes depending on where we are in space, in the region between capital R over 2 and R, so R is greater or equal to capital R over 2, we have this charge density, but this it's less or equal to capital R. So in this spherical region, we have the charge enclosed in the region R less or equal to capital R over 2. And then we have the extra charge that comes from this charge distribution between capital R over 2 and R. Okay, so let's find the charge Q in the region R less or equal to capital R over 2. That's the first contribution. It is 720 Q divided by 233. Then we have, remember here on the right side of this, we had this charge enclosed divided by epsilon 0. So if you don't consider epsilon 0, this is the charge enclosed, 720 Q r to the fourth power divided by 233 capital R to the fourth power. So we have r to the fourth power divided by capital R to the fourth power, evaluated at r is equal to capital R over 2. This is the charge enclosed by the full sphere with radius capital R over 2. So this will give me 720 Q divided by 233 capital R to the fourth power, capital R to the fourth power divided by 16. When I substitute for R, capital R over 2, R to the fourth power will cancel out, and I will be left with 45Q 45 capital Q divided by 233, because this 720 divided by 16 is 45. Or I can say, because capital Q is 233 pi capital R cube alpha over 480, I can substitute that for Q and find the answer in terms of alpha. So I can say alpha pi capital R cube alpha pi capital R cube is 480Q over 233. So for Q, we can substitute this result. Q is 233 pi alpha R cube over 480. And then this is multiplied with 45 over 233. So 233s will cancel out. And I will find 45 over 480 alpha pi R cube. This is equal to 3 alpha pi capital R cube over 32. And this can be also written as 3 over 128 if I multiply top and bottom with 4 pi alpha capital R cube. Okay, so the charge enclosed in the region R less or equal to capital R over 2 is 45 capital Q over 233, or it can be written in terms of alpha this way. Now, if I go back to Gauss law, E times 4 pi R square is charge enclosed divided by epsilon 0. Let's work on that equation. Electric field magnitude times 4 pi R square is the charge enclosed in the region R less or equal to R over capital R over 2, which is 3 over 128 4 pi alpha capital R cube divided by epsilon 0. And then I have the contribution from this region between capital R over 2 and R. And that will give me 4 pi alpha over epsilon 0 r prime squared dr prime. That's the first integration here. So this will give me alpha over epsilon 0 4 pi, the first term, r prime cube divided by 3. And then I have r prime square multiplied with r prime square. So that's going to be r prime to the 4th power. When integrated, this will give me r prime to the 5th power divided by 5 capital R square. And all of this will be evaluated between capital R over 2 and R to get the final answer. So we have E times 4 pi R square is equal to 3 over 128 times 4 pi alpha capital R cube over epsilon 0. That's the charge in the region R less or equal to capital R over 2. Then we have, if I multiply top and bottom with capital R cube, this will be 4 pi alpha capital R cube over epsilon 0. Here I have R cube divided by 3 capital R cube because I have multiplied top and bottom with R cube. And then evaluate that capital R over 2. This will give me minus capital R cube divided by 3 times 2 to the third power is 8, 24 capital R cube minus, now I'm evaluating this term at R to the fifth power, R to the fifth power divided by 5 capital R square, but I have multiplied top and bottom with R to 3, so this is 5R to the fifth power, and minus becomes a plus. Now I'm substituting capital R over 2, so this is going to give me capital R to the fifth power, and then 2 to the fifth power is 32 multiplied by 5 is 160, and then I have capital R square multiplied by capital R cube, capital R to the fifth power. Now you can see that this capital R cube in this term and this term will cancel out, and then capital R to the fifth power in this term will cancel out with the bottom expression. So if I continue working on this, I have E times 4 pi R square is equal to the charge enclosed 3 over 128 4 pi alpha capital R cube over epsilon 0, that is for R less or equal to capital R over 2. And then here I have 4 pi alpha capital R cube over epsilon 0. The result of the integration gives me R cube over 3 capital R cube, that's the first term. R cube divided by 3 capital R cube, and then I have the second term minus R to the fifth power divided by 5 capital R to the fifth power, that is this term. Then I have minus 1 over 24 and plus 1 over 160, so here I have plus 1 over 160 and minus 1 over 24. And if I work on this, this part is basically equal to 3 over 480 if I multiply it by 3, top and bottom by 3, and minus 20 over 480 if I multiply top and bottom with 20. So this will give me E times 4 pi R square is equal to 3 over 128 4 pi alpha capital R cube divided by epsilon 0 plus 4 pi alpha capital R cube divided by epsilon 0 R cube over 3 capital R square minus R to the 5th power divided by 5 capital R to the 5th power minus 3 minus 20 gives me minus 17. So minus 17 over 480. All right. And now I put all of this in 4 pi alpha capital R cube over epsilon 0 parentheses. So this will give me E times 4 pi R square is equal to 4 pi alpha capital R cube over epsilon 0. The first term here is 3 over 128. Then I have minus 17 over 480. Then I have R cube over 3 capital R square. Then I have minus R to the 5th power divided by 5 capital R to the 5th power. So if I work on this one, this is multiplied by 5, 45 over 1920, and this is multiplied by 4, 68 over 1920. So that gives me E is equal to, now I can divide by 4 pi R squared to obtain the magnitude of the electric field. Alpha capital R cube divided by epsilon 0 R squared, because these 4 pi's have disappeared. Then I have R cube divided by 3 capital R square minus R to the 5th power divided by 5 capital R to the 5th power. And 45 minus 68 is minus 23. Minus 23 over 1920. So I can now report my final answer in terms of capital Q. So I will substitute for alpha 480 capital Q over 233 pi capital R cube. So the electric field in the region capital R over 2 less or equal to R less or equal to capital R is given by, let's take this to the left side a little bit to open up space, 480 Q, 480 Q, so I'm substituting for alpha, divided by 233 pi epsilon 0 R square. So 480Q, 233 pi. There was the R cube on top, but alpha multiplied by R cube is what we're considering here. Alpha multiplied by R cube is 480Q over 233 pi. Okay, and then we have r cube divided by 3 capital R cube minus r to the fifth power divided by 5 capital R to the fifth power minus 23 over 1920, and all of this is in r hat direction. Okay, so that is basically the answer for r between capital R over 2 and capital R. How about the other region for, let's open up some space here. If I consider this region for r greater or equal to capital R, the charge enclosed will be the total charge, capital Q. So the electric field for r greater or equal to capital R will just be equal to K capital Q over R square in R hat direction. It will be the same as a point charge that carries a charge capital Q. All right, so that completes the analysis for this part. So we've looked at the first region of space, r less or equal to capital R over 2. First, what we did was to write the charge density in terms of capital Q and capital R. So for that, we have substituted the answer we have found in part A for the charge density. And then we write Gauss law, closed surface integral E dot dA is E times 4 pi r square, which is the charge enclosed divided by epsilon 0. To find the charge enclosed, we integrate the charge density, volume charge density dV in the region between 0 and r, where r is less or equal to capital R over 2. And this gives us an answer that depends on r. And when we write the Gauss law, E times 4 pi r square is charge enclosed divided by epsilon 0, we obtain our answer, which is proportional to r square in r hat direction. For capital R over 2 less or equal to r less or equal to capital R, we do the same procedure. We write for alpha the answer from part A, and then we do the Gauss integral E dot dA. E times 4 pi r square is charge enclosed divided by epsilon 0. The charge that is enclosed by this surface is the total charge in the region r less or equal to capital R over 2, plus the contribution for r between capital R over 2 and r. And there we have a different charge density. So charge density multiplied by 4 pi r prime squared dr prime dv. And when we perform this calculation for q r less or equal to r over 2, because we already know the charge enclosed is 720 q r to the fourth power over 233 capital R to the fourth power, we substitute for r capital R over 2. This just gives us the answer we're looking for, 45 q over 233, or this can be written in terms of alpha this way. And then we perform the rest of the integration here, which also gives us an answer that can be written in the parentheses 4 pi alpha capital R cube over epsilon 0. And then when we do this calculation, we obtain our final answer for the electric field. And in our final answer, because we don't want alpha, we substitute for alpha the answer from part A. So we obtain this result. So here, this is in r hat direction. And for the rest of the space, capital R greater or equal to capital R, all of the charge is enclosed. So we have E times 4 pi r square is equal to Q over epsilon 0. That's Gauss law. And that just gives us KQ over R square in R hat direction.